everyone. Let us try to understand Riemann integral, the theory of Riemann integral. Suppose that we have any surface bounded by, let's say, any curve. We have a surface bounded by any curve, and we need to find the area enclosed by this this curve. What we can do is, in order to find the rough area, then we can just draw a square or a rectangle like this. Then we can find, or we can if we know the length of this one and the length of this one, then if we multiply it, then we will get the area almost, or the rough area of this, the area bounded by this curve. In order to be more precise to our calculations, then what we can do is we can draw multiple lines like this, horizontal, and also vertical lines like this, and if we add all the squares inside this curve, then we will be a little bit closer to the actual area bounded by this curve. The more the number of lines that we draw, vertical and horizontal, then we will be more and more we will be reaching to the actual area bounded by this curve. This theory is very similar to the theory that we are going to study. That is, suppose that we have a bounded function. We have a bounded function. Let's say like this, any bounded function. Then suppose that we have a point here B and a point here at A. This is f of x, and we are asked to find the area bounded by this curve, this line, and this line. So if we are asked to find the area bounded by this curve, then what we can do is we can divide the interval AB into, let's say, suppose we first divide it into three intervals. Suppose I say this one is T1 and suppose this one is T2. Then in order to find the rough area, then I can suppose, let's say this function, this f of x, has a maximum here in this interval, a maximum here in this interval, and this point B, capital M1, and the function f of x has a maximum M2 here in this interval, and in this interval T2 to B, the function has a maximum here. Okay, now suppose we are multiplying M1 and T1 minus A. My M1 is the length of this one, the length from here to, from this line to this line. So if I draw like this, then we can see that my M1 is this one, the length from here to this line to here, and my T1 minus A is that T1 is the length from here to here, and A is my length from here to here. So T1 minus A will give me the length from here to here. So if I this multiplication, M1 and T1 minus A, give me the area of this one. And my M2, let's say this one is M2, this is M3. My M2 is the length of this line from this line. That means this line. Then my T2 minus T1 is the length of this line from here to here. So if I multiply this is M2, sorry, M2 and T2 minus T1, I will get the area of, this one. So next, if I multiply M3 with, M3 is the length of this line, M3 with B minus T2, then this will give me the area of this one. So if I add all this up, if I add all these three areas, then I will get the rough area of the surface bounded by this curve, this line, and this line. It is inaccurate. This region must not be included if we from the actual area. This region should not be included from the actual area. This region must also be it must not be included from the actual. This region also. So let's talk about the other rough area. So let's try to draw a small one here, similar to this one. I have this one. This is f of x. This is x. I'll try to draw similar to the previous one as far as possible. Let's say this is B, this is A, this is T2, and here I have T1. Now I call the minimum of f of x in this interval as m1. Here we have the minimum here, small m1, and the minimum of this of f of x in this interval is here, and the minimum in this interval is here, m3. Now, as before, I am adding up m1 into T1 minus A. This will give me again the area of this one, and my m2 into T2 minus T1 will give me the area of this one, and my M3 into B minus T2 will give me this area, this area. So this is also another rough area. Okay, so likewise we can have so many rough areas depending on the intervals that we make, the number of intervals that we make. Now suppose that let's look at this same function again. This is f of x, this is x, sorry, this is x, and we have the function is like this. Okay, here is my b, and here is my a. Here is my a. So now I am dividing that, or I have a partition. We say a partition of AB, the interval AB, is like this. I call A as T0. I call this one as T1. I call this one as T2. This point as T3, and etc. And so I have so many interval points between A and B. That is, the partition between A and B are such that let us assume that this has this, and we partition into n intervals. I call this B as Tn. Now what we can see is that if I assume that the maximum in this interval is m1, the maximum in this interval is m2, the maximum in this interval is m3, and if I multiply with the interval again, then like I will get in the first multiplication, that is m1 into I will call it T1 minus T0 now instead of A. So this will give me the area of this one. The second will give me the area of this one, m2 into T2 minus T1. My third will give me T3 minus T2. This will give me again this area. So if I continue like this, and I reach Tn minus 1, then I will be very close to the the actual area bounded by this curve, this line, and this line. So I will call this sum as UPF. And likewise, I also add up the minimum. I call the minimum here as M1, the minimum here as M2, the minimum here is M3, and so on. Then I multiply with the intervals. Then here also I'm getting the area very very close to the actual area bounded by this curve. So if I have the number of if I increase the number of this interval, then I will be more closer and closer to the actual actual area bounded by this curve. Now for different partition, like we seen before, there is 3 partition. For that 3 partition, my UPF will be different. If I have 10 partition, my UPF will be different. If I have 20 partition, also my UPF will be different. If I have like 1000 partition, also my UPF will be different. So for all those UPF, I say that the minimum or the the minimum of that UPF, I call it as infimum of UPF, where P is a partition. P is a partition on interval AB. So for those different numbers of UPF, I call the minimum as infimum of UPF, and I say that this is upper integral, and also for LPF I will have different values for different partition. And so the maximum one, I call the maximum value, I call it as supremum. I denote it like this: LPF. The maximum of the partition, the maximum of the value of this LPF, where this for a partition P, for any partition P, I denote it as supremum, and I denote like this as like this, and I call it as lower integral. So now we have 2 different values here and another different values here. This is the smallest of the values of UPF, because UPF can have different values for different partitions, and the maximum of this LPF, I call it as I denote it as like this, lower integral, and because I'm going to have different values for LPF, so it may happen that these 2 values are equal. It can happen that these 2 values are equal. Then I say that, then we can say that the function f of x is Riemann integrable. So if these values and this value and this value are equal, then we say that the function f is Riemann integrable. Then we also denote the value of this one as integration of, we also denote like the value of this one as integration of f of x dx. So this implies the function f is Riemann integrable. That is all the theories lies in the Riemann integral. Thank you.